Hello and welcome to this presentation related to geometric progression, often stated as GP for short. It should be noted there is a previous presentation related to arithmetic progression, AP, which it strongly encouraged you reviewed before reviewing the contents of this presentation. Here's an overview of the presentation. We commence with an introduction to geometric progression, stating here the nth term in the GP. Formula is nn is equal to a times r to the power of n minus 1. Here's a nomenclature used throughout the presentation. Again, referring back to our previous presentations on arithmetic progression, with APs we have a common difference between each term in the series labelled lowercase d, but with geometric progression we have a common ratio between each successive term in the series, and that's labelled r. As with the AP problems, with geometric problems we sometimes require to summate a geometric progression, and here we have two formulae for summating terms in a geometric progression. Sn is the summation notation, so we have this general form on the left hand side, and when the common ratio is greater than -1 but less than +1, we have a simplified formula we can use for summating terms in the series. We often call this latter summation formula summation to infinity, summating all the terms in the series when r has a magnitude of less than 1. And here are the approximate start times related to the introduction to geometric progression and summation of a geometric progression. Please note these times are rounded to the nearest minute. Presentation overview continued. We then include an array of tutorial exercises extracted from your workbook. Here's exercise 1A through to exercise 4A. Answers to each of the exercises shown in the brackets on the right hand side. The question. Just note within exercise 4 there's a hint that we should use the third law of logarithms to solve for the index n as required in the problem stated. Laws of log shown here for reference, third law. Note, full work solutions are included for these exercises. Again, here are the approximate start times related to exercise 1 through to exercise 4A, all times rounded to the nearest minute. Tutorial exercises continued, exercise 5A through to 7A, and again answers stated on the right hand side. Just noting exercise 7A there are actually two GP series to determine, and again full work solutions are included for exercise 5A through to 7A. Here are the approximate start times related to exercise 5A through to 7A. Presentation overview continued, and here are a few further tutorial exercises, exercise 1B through to exercise 3B. Again, answers on the right hand side here. Full work solutions are included for exercise 1B, 2B and 3B. And here are the approximate start times related to exercise 1B, 2B and 3B. Again, all times are rounded to the nearest minute. Presentation overview continued. And here are some tutorial questions related to geometric progression problems for you to review at your own pace. Questions 1 through to 3, and answers as always shown in the brackets on the right hand side here. And for your reference, here is the approximate start time of these tutorial questions. And you're left with tutorial questions to attempt at your own pace. Answers stated in the brackets on the right hand side. Geometric progression, or GP, has a constant ratio between successive terms in the series. This common ratio is denoted by the symbol r. So in the following series, 1, 2, 4, 8, 16, etc. has a common ratio of 2. In other words, multiplying 1 by 2 we get 2, multiplying 2 by 2 we get 4, 4 by 2 we get 8, and so on. In the next series, 1, 3.5, 12.25, etc. the common ratio there is 3.5. Each term is multiplied by 3.5 to get the following term. In the next series we have 4, 1, quarter, 1/16, etc. The common ratio here is a quarter, or 0.25. In other words, each term is multiplied by a quarter to get the following term. So 4 times a quarter is 1, 1 times a quarter is a quarter times a quarter is 1/16, and so it goes on. Next series we have 2, -4, 8, -16, 32. The common ratio here is -2. In other words, each term is multiplied by -2 to get the following term. 2 times -2 is -4. -4 times -2 is +8. +8 times -2 is -16. So we have a change of sign, a plus minus, because the common ratio is -2. And in terms of algebra, the series a, ax, ax squared, ax cubed, the common ratio there is x. Each term is multiplied by x to get the next term. A times x is ax times x is ax squared, and so on. Each of the GP progressions on the previous slide can be represented by the equation nn is equal to a times r to the power of n minus 1, where nn is the value of the n term in a series, a is the first term in the series, r is the common ratio for the series, and n is the number of terms we are considering, or the number of terms in the series. Example 1 shows us how to apply the GP formula. We're given a series 4, 8, 16, 32, and we're asked to find the fifth term, which we can see is 64, and the 10th term, which will be the 2048, looking at the series given. We're going to use the formula to derive these terms. So noting that a in this case, the first term in the series is 4, the common ratio is actually 2 from the series, but if you don't know what the common ratio is, it's always the second term divided by the first term, so 8 divided by 4 will give me 2 in this case. And if I want to find the fifth term in the series, then little n is equal to 5. So trying to find big N 5 here, it's equal to the a, which is the 4, multiplied by the common ratio r to the power of n minus 1. So that's basically 4 times 2 to the power of 4. It gives me 64. Just watch your bod maths here, do the 2 to the power of 4 first before multiplying by the 4. For the 10th term, n is equal to 10 in this case, so the big N 10 is equal to, again, the a times the r to the power of n minus 1. N is 10 in this case, so we end up with 2048. And we can see that's correct from the above sequence. Example 2 is an illustration of how to apply the geometric progression formula. If inflation is assumed to be constant at 3%, what will £1,000 at today's value be worth after 4 years to the nearest pound? So this is a geometric progression problem. So we're going to use the nn is equal to the ar to the n minus 1 formula. In this case, the a, the initial term in our series, would be the £1,000. Now it says it wants to find the value of the £1,000 subject to this inflation rate after 4 years, so that means in the 5th year. So n is equal to 5 here. Now the inflation is a depreciation, an annual depreciation. To find the r factor here, what we will do is have 1 take away the inflation rate, 1 take away 3%. Don't forget 3% is actually 0.03 as a value. So 1 take away 0.03 gives me 0.97. So that's the common ratio. So for each year, the sum of money is multiplied by 0.97 to get the value in the next year. So using our GP formula, nn is equal to the a, which is 1,000, multiplied by 0.97 to the power of n minus 1. And in this case we said was going to be 5, so that will be basically 1,000 times 0.97 to the power of 4, which gives us a value of £885. You can see in the table below that's the value at the beginning of the 5th year due to the deflation rate of 3%. Sometimes we want to summate geometric progressions, and we have a formula to do this. There's a proof here for you, which I will leave you with if you want to follow the proof through, but I'm going straight to the bolded box equation here. This is the formula for summating a number of terms in a geometric series. The formula is Sn is equal to a, the first term, multiplied by, in brackets, 1, take away r to the power n, the common ratio to the power n, all divided by 1 minus r, 1 minus the common ratio. We're going to look here at a summation formula where the R value is between -1 and +1. In other words, the magnitude is less than 1. What we will find here is that this term in the series, the R to the power n on the top line, will tend to 0. So R to the n tends to 0 for values of R between -1 and a +1. If you just think of this numerically, if you had something like a half, 0.5, raised to a power of a really large number, say 100, you'll find that that's practically 0. For all intents and purposes, that is 0. So as the n becomes really big, and we've got a value of R between -1 and +1, that term basically disappears, and we end up multiplying the a on the top line by 1. So we often call this formula sum to infinity when we're summing all the possible terms there are in a GP series. The sum to infinity equation is simply a divided by 1 minus r, but is only applicable when the r ratio is between -1 and +1. Here's an example of using the sum to infinity equation. Example 3 shows a series of 1, a half, a quarter, and an eighth, and so it goes on. In other words, each term there is multiplied by a half. The a in this case is equal to 1, the r is equal to the second term divided by the first term, so half divided by 1 is a half. So each term is multiplied by a half to get the next term. This is a sum to infinity problem, and if we use the s to infinity, we simply have a upon 1 minus r, putting our figures in, that's 1 upon 1 minus a half. We will find that the total value is 2 for sum to infinity. If you look at the graphical representation below, you can see that as the terms in the series increase, they become smaller and smaller and smaller, and they tend towards 0. And you can see that the summation of the terms in the series is approaching the value of 2 and plateaus out on the value of 2. Example 4 here is another summation problem. We're told at the beginning of each year £1,000 is to be invested. The compound interest rate is 4.3%. We've got to find how much this will be worth in the 5th year. So this is an SN problem here because we're actually putting £1,000 into the investment every year. We start with £1,000, that includes interest for the first year, and the next year we add another £1,000 to this on top of the accrued interest of the £1,000, and so it goes on. So the first term in the series here would be 1,000, and the number of terms in the series will be 5 because the question says it wants the value in the 5th year. So the R ratio here will be 1 plus 4.3% because this is an investment, we've got interest added to our investment. So that will be 1 plus 0.043, so 1.043 is the R ratio here. So we're using summation here because we're adding up the value of the fund after each year. Don't forget we're adding £1,000 to it every year ourselves. So 1,000 times by 1 minus 1.043 to the power of 5 on the top line there, divided by, on the bottom line, 1 minus 1.043. That's our formula, a times 1 minus r to the n over 1 minus r. If we do the arithmetic on that, we find the summation in the 5th year is 5,449. And in the table below, I've shown a breakdown of how adding £1,000 each year to the investment, that value is arrived at. Example 5. A job is advertised with a starting salary of £12,000 per year and an annual increment of 5%. We've got to find out what the salary will be in the 10th year and what would be the total sum earned by the end of the 10th year. So, first part of the question, we're going to use the NN equals A R to N minus 1 formula. We know that the first term in this series, A, is the starting salary, that's £12,000, and the R ratio here will be 1 plus the 5%, the annual increment, which is 1 plus 0.05 or 1.05. So the R value is 1.05. Our formula then will be NN is equal to 12,000 times 1.05 to the power of n minus 1. If we're looking for the value in the 10th year, then n will equal to 10, and we will put 10 into the equation. So n10 is equal to 12,000 times 1.05 to the power of 10 minus 1. Doing the numbers on that, we find in the 10th year the salary is worth £18,616. Below I've shown you a breakdown of how each year the salary is increasing, and it shows in the 10th year it's £8,616. Example 5 continued, part 2 here. We've got to sum the amount of money earned in the 10 years. So n will be equal to 10 this time, and we'll use the Sn equation because we're going to add up the value of the salaries in every year to find the total salary earned in the 10th year. So in this case S10 is equal to 12,000 times, in brackets, 1 take away the 1.05, the R value to the power of n, which is 10, divided by 1, take away 1.05, the R value. We do the numbers on this. The salary earned in the 10th year in total is £150,935. Below in the table I've shown the salaries added up per year, and we find by the 10th year we get £150,935. Exercise 1A. We're asked to find the 10th term in the series 3, 6, 12, 24, etc. We're going to use the geometric progression formula nn is equal to a times r to the n minus 1. From the series we can see the first term a is equal to 3. The common ratio r is equal to the second term divided by the first term, so 6 divided by 3 in this case is equal to 2. We're trying to find the 10th term in the series, so little n is equal to 10. Therefore n10 is equal to the a, 3, times the r, 2 to the power of n minus 1, 10 minus 1. Doing the arithmetic on this, n10 is equal to 1536, or the 10th term in the series is 1536. Exercise 2a. We're asked to find the sum of the first 7 terms in the series, half, 1 1/2, 4 1/2, 13 1/2, etc. So we're going to sum the first 7 terms. The a term in this case is the first term in the series, which is a half. I'll write that as 0.5. Common ratio r is equal to the second term divided by the first term, so 1.5 divided by 0.5 in this case will give me 3. I'm going to use the Sn equation to summate the terms. The equation says a times open bracket 1 take away r to the n close bracket divided by 1 minus r. So S7 in this case will be the a, 0.5, multiplied by in brackets the 1 take away the r to the n, so that's 3 to the 7 divided by 1 take away r, which is 1 take away 3. Doing the arithmetic, S7 is equal to 546.5, or the sum of the 7 terms is 546.5. Exercise 3a. The first term in the geometric progression is 12, and the 5th term is 55. We're asked to find the 8th term and the 11th term in the series. So, using the formula nn is equal to ar to the n minus 1, we're using this formula because we're finding specific terms in the series. We know that a, the first term in the series, is 12, given in the question, and the 5th term, n5, is 55. What we do not know at the moment is the common ratio r. Okay, so the first thing we need to do is to find the common ratio r here. I'm going to consider the 5th term to do this. For reference, just note the formatting shown here. So n5 in this case is 55, and that's equal to a, which is 12, multiplied by r to the power of n minus 1. That's 5 minus 1. Rearranging the equation, that's 55 divided by 12 is equal to r to the 4. If I take the 4th root of both sides of the equation, the 4th root of 55 divided by 12 is equal to 1.4632. We now have our value of r. Exercise 3a. Now we know the value of constant ratio r, we can find the 8th term in the series, when little n is equal to 8. So from our formula nn, n8 in this case is equal to the a, the 12, multiplied by the r value, the 1.4632, to the power of 8 take away 1. Doing the numbers on that, n8 is equal to 172.3. So the 8th term in the series is 172.3. Find the 11th term in the series, now little n is equal to 11, and we go through exactly the same process, just putting the 11 for the n. The 11th term in the series is 539.7. Okay, exercise 4a here. We're given a series of 2187, 729, 243, and we're asked to find where in the series does 1 upon 9 occur. What's the little n value, if you like, for 1 upon 9? Is it the 10th term or the 100th term we're trying to find? The suggestion here is to use logs to solve for the little n value. So we're going to use the nn equation here because we're finding a term in the series. We know the nn value, it's 1 upon 9. We're trying to find the little n value here. So we're going to use the nn equals to ar to the n minus 1, and we're solving for little n. From the series given, the first term a is equal to 2187, and the common ratio r is always the second term divided by the first term. So in this case it's 1 upon 3, or if you want to use decimals, it's 0.3 recurring. So my nn equation here is 2187, in brackets the 1 upon 3, all to the power of n minus 1. Now we've got to find the value of little n when the nn is equal to 1 upon 9. So on the left hand side of the equation for nn, I put the 1 upon 9. So 1 upon 9 is equal to 2187 times my third raised to the power of n minus 1. And I'm trying to find little n. On the next line I've just divided both sides by the 2187. And on the next line I've just simply worked out the value of 1 divided by 9 divided by 2187 to give me this number here. Exercise 4 continued, so I've just repeated this line for convenience. So what we're going to do now to solve for the little n value is to take common logarithms, that's log to the base 10, of both sides of the equation. So taking log of the left hand side of the equation, I take log of the right hand side of the equation. So I'm in log domain. I'm going to apply the third law of logs here to solve this equation. Now the third law says if you have something in the format of log a to the n, which is my log 1/3 to the power of n minus 1, I can write it as n log of a. So in this case on the right hand side of the equation, I can take the n minus 1, which is the n in the third law, and multiply it by the log of 1/3. On the right hand side I simply worked out the log of the 50.805 times 10 to the minus 6, and that's minus 4.29409. On the next line I simply worked out the log of a third for my calculator, so minus 0.4771212, and on the subsequent line I've worked out that n minus 1 is equal to the minus 4.29409 divided by the minus 0.447, etc. Doing the numbers on that, you'll find that n is equal to 9 plus 1, the n is the 10th term. So in other words, the 1 upon 9 is the 10th term in our series. Okay, exercise 5a here. We're asked to calculate the sum of the first 9 terms of the series, 72, 57.6, 46.08, etc. So the first term in the series, a, is equal to 72. The common ratio is the second term divided by the first term, so that's 0.8 in this case, and the little n is 9. We'll use the Sn equation equals to a open bracket 1 minus r to the n, or divided by 1 minus r in this case. We've got a discrete number of terms to summate. So simply using the equation, S9 is equal to the a 72 times 1 minus the r to the n, so that's minus 0.8 to the power 9 in this case, divided by 1 minus the r minus the 1 minus the 0.8. I'll let you look at the numbers and you'll get the value of S9 is equal to 311.7. Okay, in exercise 6 we're asked to sum to infinity here the series 3, 1, 3, etc. So in this particular case, the a, the first term, is 3. The common ratio r is equal to the second term divided by the first term, so it's the third one divided by 3 here. And the n is effectively infinity here, all the terms. Now because the r value is between minus 1 and plus 1, we can use the simplified equation Sn is equal to a divided by 1 minus r. So this is the sum to infinity. So in this case, the sum to infinity, the S infinity is equal to the a, which is 3, divided by the 1, take away the r, which is the third, and that gives you 4.5. So summing all the terms in this series to infinity will give you a value of 4.5. Exercise 7a. The geometric progression has its third term, a value of 12, and its fifth term, a value of 48. We're asked to find the common ratio, the r value, the first term in the series, the a value, and then state the first 5 terms in the series. So in this particular question, we do not know a and we do not know r. We are given the third term, n3, is equal to 12, and the fifth term, n5, is equal to 48. Using the geometric progression formula, Nn, I can create 2 simultaneous equations. So if we consider the third term, the 12 value on the left hand side, that equals to a r to the power of n minus 1, that would be 3 minus 1. Simplifying that, 12 is equal to ar to the 2. If I rearrange that, I get a is equal to 12 divided by r squared, and I've called that equation 1. If we consider the fifth term in the series, we're told that's 48, that's equal to ar to the 5 minus 1. Little n is equal to 5 here. Simplifying, we get 48 is equal to ar to the 4, and I've called that equation 2. Exercise 7a. I just repeated equation 1 here and 2 for convenience. So now if we substitute equation 1 into equation 2, we get 48 is equal to 12 divided by r squared, that's the a value from equation 1, and that's multiplied by the r4. Using my laws of indices, that simplifies to 48 is equal to 12 r squared. In other words, r to the 4 divided by r squared gives me r squared. Rearranging the equation, dividing both sides by 12, I get r squared is equal to 4. So r in this case is the square root of 4 plus or minus 2. Don't forget when we take a square root, there are always two answers. If I put the value of r back into equation 1, I get a is equal to 12 divided by r squared, that's 2 squared, that gives me 4. So 12 divided by 4 gives me 3. So I've got the value of a is equal to 3. Using the value of a, I can now find the series using a r value of plus 2, I will get 3, 6, 12, 24, etc. And using the value of r of minus 2, I will get 3, minus 6, 12, minus 24, etc. The alternating pattern there is because of the negative r value. I'll let you think that through. Exercise 1b. In a geometric progression, the sixth term in the series is 8 times the third term, and the sum of the seventh and eighth terms is 192. We're asked to find the common ratio, the r value, the first term in the series a, and then sum the 5th to the 11th terms inclusive. So from the geometric progression equation, nn is equal to ar to the n minus 1. We know that the sixth term is 8 times the third term. So using mathematical notation here, I could write n6 on the left hand side is equal to 8 times n3 on the right hand side. I'll let you think that through. If I put the equation in for n6, we get ar to the n minus 1, ar to the 6 minus 1 is equal to 8 times ar to the n minus 1, ar to the 3 minus 1. On the next line, I get r to the 5 equals to ar squared. Notice the a's have cancelled because they're common to both sides of the equation. Dividing throughout by r squared, I get r cubed is equal to 8, and the cube root of 8 gives me a value of 2. So my r value is 2. Exercise 1b continued. So from the question we know also that the sum of the 7th and 8th terms is equal to 192. So in this case, mathematically speaking, I can write n7 plus n8 is equal to 192. I'll let you think that through. If I put the formula in for n7, I would get ar to the 7 minus 1, n minus 1 there, plus ar to the 8 minus 1, the n minus 1 again, is equal to 192. If I factorise on the a, because a is common to both terms, I would get a outside the bracket, and inside I would get r to the 6 plus r to the 7, and that's equal to 192. We know that r is actually 2, so I can just replace the r's by the 2's here. If I work the bracket out, I get a times 192. So 2 to the 6 plus 2 to the 7 is 192. That's still equal to 192. We can obviously see here that that cancels, so we get a is equal to 1. Okay, exercise 1b continued here, part 3. We're asked now to sum the 5th to the 11th terms inclusive. So I'm going to use the Sn equation now. I'm going to first of all sum the first 11 terms in the series, S11. Then I'm going to sum the first 4 terms in the series, S4. Then I'm going to take S4 from S11 to find the summation of the terms 5 to 11 inclusive. So summating the first 11 terms, my S11 term, it's a, which is 1 in this case, open bracket, 1 take away r to the 11, so that's 2 to the 11, divided by 1 minus 2. that works out to be 2047. So summating the first 11 terms in the series is a value of 2047. If I summate the first 4 terms in the series, S4, again using the same formula, but this time the n is equal to 4, not 11, I get a value of 15. So summating the first 4 terms in the series gives me 15. Simply taking 15 from 2047 gives me the value of the terms 5 to 11 inclusive, which is 2032. Exercise 2b. A hire tool firm finds that their net return from hiring tools is decreasing by 10% per year. If their net gain on a certain tool this year is £400, we've got to find the possible total future profits from this tool, assuming it lasts forever. This is a sum to infinity problem. We're going to try and add up all the possible terms in the series. So the first term A is equal to £400. That's what they've earned this year. The R value here, the common ratio value, will be 1, take away the 10% that the profit is decreasing per year. So take away 0.1 in this case. So the R value is 0.9. My sum to infinity equation is simply the A value divided by 1 minus R. So the A in this case is 400, and then 1 take away 0.9, the answer is £4,000. £4,000 is the maximum possible profit they could make if the tool lasts forever. Exercise 2b. This is just for reference only. We're going to use the Sn equation, which relates to a specific number of terms to summate. If we looked at n was equal to 10, then summating the first 10 terms of our series, the profit would be £2,605. If we looked at n is equal to 50, so the tool is lasting 50 years now, the profit would be £3,979. If we now go to 100 years, n is equal to 100, the profit would be £3,999.90. You can see that the summation tends to £4,000 as the n value gets larger and larger. Exercise 3b. £100 is invested at a compound interest of 8% per year. We've got to find the value of this after 10 years and the time, correct to the nearest year, it takes to reach more than £300. So don't forget, after 10 years means in the 11th year, and we'll use logs for the second part of the question. So looking at the first part of the question, I'm going to find the value of the fund after 10 years. That's when n is equal to 11. So the formula I'm using is nn is equal to ar to the n minus 1, where a is the initial £100, and the common ratio here is 1 plus the 8%, 1 plus 0.08 is 1.08. So our geometric progression formula nn will be 100 multiplied by 1.08 to the power of n minus 1. Exercise 3b continues. So part 1, we've got to find what the investment is worth after 10 years, that's in the 11th year. So n is equal to 11 here. So n11 is equal to the a times the r to the power of 11 minus 1. Doing the numbers on this, we find that the value after the 10 years is 215.89. The table shows the investment after each of the years at an 8% interest rate, and we can see after 10 years in the 11th year it's worth £216. Exercise 3b here continued, part 2. We're asked to find now the number of years, little n, it takes for the £100 investment to reach £300. So the £300 is our nn value in our equation. So from the GP equation, nn is equal to ar to the n minus 1. On the left hand side I have 300 for my nn value. On the right hand side 100 for the a, and the r is 1.08 to the power of n minus 1. And it's little n we're trying to find. All I've done on the next line is divide both sides by 100, so 3 is equal to 1.08 to the power of n minus 1. To solve for n, I'm going to use common logarithms. So I'm taking logs of both sides of the equation. So on the left hand side, log of 3 is equal to, on the right hand side, log of 1.08 to the power of n minus 1. I'm going to use the third law of logarithms here to solve this problem. So the third law states if you have a format log a to the n, which on the right hand side we do, we have log of 1.08, that's my a, to the n, in this case that's n minus 1, we can write that as n times the log of a. So on the next line on the right hand side I've written n times log of a, n minus 1 in this case, times by the log of a, log of 1.08. I'll let you think that through. Do note in this line that the n-1 had to be in brackets to ensure our BODMAS was correct. On the left hand side I have my log of 3. All I do now is rearrange the equation. So I divide both sides by the log of 1.08 to leave with n-1 shown on the left hand side here, and then I simply add 1 to both sides to find the final value of n, which is 15.275 years. In other words, the investment of £100 in year 1 reached £300 in the 16th year. So we conclude the presentation with some tutorial questions for you to undertake at your own pace. Here's questions 1 through to question 3. Again, as always, answers shown in the brackets on the right hand side here. Notice there are some hints in the questions. Encourage you to read them carefully. Hopefully that helps you generate your solutions. I'd encourage you to stop the presentation and attempt questions 1 through to 3, but I will very briefly show you the full work solutions on the following slides. Tutorial questions. Here's the full work solution for question 1. We commence from our standard geometric progression formula, and then, given the information in the question, we can find the common ratio r. We're asked to find the 8th term in the series, so lowercase n is equal to 8, and our 8th term calculated here. I'll let you review the solution at your own pace. Question 2 solution. Again, there's a hint in the question to generate simultaneous equations, so that's what we will do here. I'll let you review the solution at your own pace, but knowing the 2nd term in the series, we can generate one equation, rearrange here, called equation 1, and knowing the 5th term in the series, we can generate a 2nd equation, shown here. Question 2, solution continued. Just repeated the equations from the previous slide for convenience. Essentially now we're just solving two simultaneous equations using the substitution process. I'll let you review the solution at your own pace, but you should find that a is equal to 1 in this case. And by substituting into equation 1, we can find the value of r, -3. So again, we can find the 8th term in the series n8, shown here. And question 3, commencement of the solution. Again, stating the formula for the GP here. I'll let you review the solution at your own pace. But essentially on this slide we calculate the value of the common ratio r. And question 3 solution continued. Once we found the value of r, we can use our standard formula for nn to calculate the geometric means n2, n3 and n4, shown here. Finally, we state the full geometric progression for clarity. Finally, questions 4 through to 7 for you to attempt at your own pace and develop your own solutions, but the answers are shown in the brackets on the right hand side. Here's the bibliography used to help generate this presentation. Some very good technician engineering textbooks stated here. I hope this presentation has been of interest to you, and thank you for viewing.